Hello, today we're going to talk about lesson 3 on enthalpy, entropy, and free energy. So if you look behind me, you'll see the definition for enthalpy, the amount of energy either released or absorbed as heat during a chemical reaction. Now, we're going to use positive and negative symbols to describe whether heat energy is going into a reaction and it's endothermic, or heat energy is coming out of a reaction as a product, an exothermic reaction. You take a look at the first example behind me. In this first example, you'll see that we have a delta H for the reaction, which means change in heat energy for the reaction. This part up here just means at standard conditions. And standard conditions for enthalpy reactions are 1 atmosphere of pressure and 298 Kelvin. So slightly different than what standard conditions were when we talked about gas laws. So if you look at this reaction, it tells you that the delta H for the reaction is a positive value of 627. That means it's an endothermic reaction. Heat energy is needed in order for this reaction to occur. So the other way to write this reaction is to show that heat energy as part of the chemical equation on the appropriate side. So if it's an endothermic reaction, we would put it over here on the reactant side. In our second example, we have iron reacting with oxygen to produce iron 3 oxide. In this case, notice that the delta H for the reaction is negative, indicating that it's an exothermic reaction or that heat energy is being given off. If we were to do the same thing we did up here, that heat energy would appear as a product on the right side of the reaction. So when you go and calculate these, what you're going to do is look at the table of thermodynamic data. Now, that table has 3 different columns in it. The first column is for enthalpy, delta H. The second column is for free energy, or delta G. And the last column is for entropy. In our case, we're going to be using the first column because we're calculating enthalpy right now. So I've gone ahead and looked up the values for all of our reactant end products already, and I've listed them here on the side. So when you're calculating the enthalpy of a reaction, and we'll do the same exact process for free energy and for entropy, you're going to start on the product side. You're going to take each of the values for the 2 products in this case and multiply them by their mole amounts and then add them together. Then you're going to do the same thing on the reactant side, and then you're going to subtract products minus reactants. So let's take a look. We start over here. Our first product is carbon dioxide. So we're going to say that the delta H at standard conditions for this reaction is equal to the value for carbon dioxide. So in this case, negative 393.5. If you look at the top of the column, the units are kilojoules per mole. Next, we're going to multiply that by whatever the coefficient is from our balanced equation. So in this case, our coefficient for carbon dioxide is 3, so we're going to multiply by 3. Next, we're going to find the value for water. Value for water over here, negative 285.83. Kilojoules per mole. We're going to multiply it by its coefficient from the balanced equation, which is 4. We're going to close the brackets because we only have 2 products and we found the values for both of them. Now we're going to look at the left side, the reactant side of the reaction. So we're going to subtract. Remember, it's going to be products minus reactants. So the value for C3H8, that's up here, negative 103.85. Again, in kilojoules per mole, this time it's just times 1, plus the value for oxygen. And what we're going to find is that any element in its natural state is going to have an enthalpy value of 0 kilojoules per mole. And that's because that is how that element exists. So the formation of it doesn't require any energy. So this oxygen in this case has a value of 0 kilojoules per mole. We can go ahead and multiply it by 5, but of course, since it's 0, this whole term is just going to end up being 0. Okay, let's plug this into our calculator and let's see what we get here. So I'm going to bring up the calculator. Okay, so as I type this in, I'm going to use parentheses. So I'm going to have 393.5, which of course is negative, times 3, close parentheses, plus, open parentheses, 285.83. That is also negative. I'm going to multiply that by 4, close parentheses, close parentheses. Now we're going to subtract the other side. So we have open parentheses, 103.85 times 1. So we don't have to worry about that, but it is negative. Close the parentheses. We get this answer. So we get a delta H value that is equal to negative 2,200. I'm just going to round to 3 significant figures. So negative 2,220 kilojoules per mole. The fact that we have a negative sign here means that this reaction is exothermic, meaning heat energy is going to be given off when this occurs. Okay, let's take a look at our next slide. So now we're going to talk briefly about free energy. So it says free energy is the energy in a system that is available for work, and this value determines whether a reaction is spontaneous or not. So basically whether the reaction occurs or does not occur. Everyone assumes that when you put 2 reactants together, something's always going to happen, but that's not actually true. Sometimes when you put 2 things together, nothing happens at all. So determining whether or not a reaction is going to take place, you can do that using free energy. So if you look behind me, a delta G value that is positive means that the reaction does not occur spontaneously, and it's actually a delta G value that is negative that indicates that a reaction does occur. We are also going to look at entropy. So the entropy of a reaction determines how disordered something is. Basically disorganized. The more disorganized you are, the more likely that that reaction is going to take place. So if we look at the 2 possible values, we have positive and negative. A positive value for delta S means that disorder is increasing. It's becoming more disorganized. A negative value for delta S means that disorder is decreasing. This is not something that would occur naturally. So those reactions where disorder decreases tend not to happen as readily. Now, if we look at our 4 states of matter, so really gas, solid, liquid, aqueous is not necessarily a new state of matter. It's just a mixture of both ions and a solution. But gas is going to be the most disordered. You have molecules going around all different directions. They're very far apart from each other. Their speed is going to be extremely fast. So when we think about the amount of disorder, if you have molecules that are in the gaseous state, those are the most disordered. Then, of course, you go to aqueous solutions, liquid solutions. Aqueous is more disordered than liquids because aqueous is made up of 2 different substances, right? If you think about the water as a solvent, and then the different ions that are floating around. Liquid and then solid would be the most ordered or the least disordered. So just to kind of give you a sense, if you have a reaction where you have a solid plus a liquid and it forms a gas, the delta S for that reaction is going to be extremely positive, right? Because you have things that are not very disordered becoming something that is really disordered. However, if you have the opposite, so let's say you have 2 gases reacting and they form a solid and a liquid, in a case like this, you're going to wind up with a delta S for the reaction that is negative, because the reaction is actually, the components of it are becoming more ordered. Let's take a look at some examples. Okay, so we're going to use the very same example that we saw in our first part with enthalpy, but this time we're going to look at the values for free energy and for entropy. Notice, just like we saw before, the delta G of formation for an element in its natural state is 0 because it does not have to form. That's how it already exists. So we're going to do the exact same thing. We're going to start over here and we're going to say that the delta G for the reaction is equal to, so we're going to start with the value for carbon dioxide. Remember, we always start on the product side first. So we're going to do our two products, then we're going to look at our two reactants. So the first product we have is carbon dioxide. Its value is negative 394.4. For right now, we're only going to be using the delta G's because we're solving for delta G. So negative 394.4 kilojoules per mole. We're going to multiply that by 3 because of the 3 in the balanced equation. And we're going to add the other product, just like we're adding here. The value for water, negative 237.13 kilojoules per mole times its coefficient of 4, close parentheses, close the square bracket because we're done with the product side. Now we're going to move on to the reactant side. We have our value for propane, negative 23.47. Again, kilojoules per mole. This time we're only multiplying by 1 because there's a 1 in our balanced equation. Close the parentheses. And then, of course, just like we saw last time, the value for oxygen is 0 kilojoules per mole. We're going to multiply that by 5, just like that. So when we solve here, I'm going to bring up our calculator. So when we solve, we're going to type into our calculator 394. Use some parentheses here. So we have 394.4 times 3, negative, plus, open parentheses, 237.13 negative times 4, close parentheses, minus, because we're going to subtract the reactant side, 23.47 negative. We don't have to multiply that by anything because we're multiplying by 1, and the last part is 0. So we get our final answer of negative 2,108. So negative 2,108. Kilojoules per mole. That is our answer for delta G. Let's take a look at our values over here on the right side for delta S. So delta S, the reaction, open the square bracket. This time, because we're talking about entropy, this is kind of a made up number and everything is based against the hydrogen. So in this case, every one of our values, including oxygen, will have a number associated with it. So we're going to start again, though, on carbon dioxide. We do it the exact same way. So 213.6. Notice our unit is a little different, joules per Kelvin mole instead of kilojoules per Kelvin mole. So we're going to multiply that by 3. Then we're going to add on to that the value for water, 69.91 joules per Kelvin mole. This time we're going to multiply that by 4. Close the square bracket. On the right side, on our reactant side, we have our value for C3H8. Value for C3H8 is 269.9. Multiply that by 1, close the parentheses, and then finally our value for oxygen is 205.0 per Kelvin mole. And And of course, we're going to take that value and multiply it by 5. So we're going to type this into our calculator. So we're going to open some parentheses, 213.6 times 3. Notice that in this case, we don't have any negative values. 69.91 times 4, close parentheses, minus, open parentheses, 269.1 times 1, which you don't really have to do, plus 205.0 times 5. We get this answer, negative 373.66. So let's take a look at the meaning of the two values that we just calculated. A negative value for delta G means that the reaction is spontaneous, so it will occur. And a negative value for delta S means that the reaction is actually less disordered. So there's a decrease in disorder. Now, usually this works against a reaction occurring. However, when we compare the magnitude of both of these changes, it turns out that the reaction still does occur because of the amount of energy being given off. The other thing that you'll notice is, notice that we're starting off with 1 plus 5, 6 moles of gas. And we're converting that to 3 moles of gas plus 4 moles of liquid. So based on these numbers up here, we would predict that this in fact would lead to a decrease in our entropy, a decrease in our disorder, because we're losing moles of gas, and those moles of gas are actually being replaced by a liquid up here. Okay, so let's take a look at combining all of these different terms. So if you look at this equation relates together our free energy, so whether or not the reaction will occur, with the value for enthalpy, the very first thing that we learned, and our value for entropy, our amount of disorder. So if we take a look, first of all, a positive value for delta H, just as a reminder, means that the reaction is endothermic. Heat is going into the reaction, or heat is necessary for the reaction. These two are exothermic, meaning heat energy is being given off. Okay, on the column that has the delta S, we're going to say this is increasing disorder, meaning it's becoming more messed up. Same thing here, we have increasing disorder. For the negative values, we have decreasing disorder, meaning it's becoming more organized or less disordered. So if you think about it, the two conditions that are most beneficial, that are most likely to lead to a reaction occurring, are exothermic. So these are good things in order for a reaction to occur, and increasing disorder. So that would be here, and that would be here. So this reaction, when you have an exothermic reaction, so you have a negative value for delta H, and you have a positive value for delta S, this is going to result in a delta G that is negative all of the time. So we're going to put here that this reaction is always going to be spontaneous. This is your best case scenario for a reaction to occur. If the reaction is exothermic, meaning gives off energy, ends up at a lower energy state, and increases in disorder at the same time. The worst combination are these two. So if you have a reaction that is endothermic, meaning heat energy is required, and disorder decreases, if you put in a positive value here and a negative value here, meaning this whole term is positive, that means delta G is going to be positive, and this reaction is never going to be spontaneous. Okay, for the other two scenarios, you have to do a little bit of math. So for the first one, where we have an endothermic reaction, meaning delta H is positive, but we also have increasing disorder, meaning this is positive, but because we're subtracting it, this overall term is negative. This will end up being positive or negative depending on the amount of temperature that you have, or how high the temperature is. So the bigger this value is, the bigger this negative sign becomes, the more likely it is to be spontaneous. So we're going to say that this is spontaneous at high temperatures. So this combination can also be spontaneous. You have a negative value for delta H, meaning that the reaction is exothermic, and a negative value for delta S. So minus a negative means this whole term ends up being positive. So as long as temperature is kept low and the positive amount here is smaller than the negative amount from enthalpy, you can still wind up with a spontaneous reaction. So we're going to say that this is spontaneous at low temperature. Okay, this concludes our lesson on free energy, enthalpy, and entropy. So if you could please try, there are 2 homework problems assigned. I would like you to calculate delta H, delta S, and delta G using that table of thermodynamic data. Be careful, make sure when you choose a substance that you're using the right column on the table, and also that you're choosing the right state of matter. So sometimes the same substance, especially something like water, is present on the table as both a liquid and a gas. So you want to make sure that you're using the right state of matter. All right, if you have any questions, please stop by office hours or send me an email. Have a great week, everyone.